Back to it.
Controlling reaction rate and writing rate laws. So it's really not so much controlling, but predicting. You want to be able to happen. And if you have the conditions right, you can be a lot more effective, especially with something like drugs like Tums. You don't want the whole thing to react at once. You want it to react slowly over time. To be a lot more effective, people will buy your product. So it could be in making the product. It could be as the product operates in you, whether they're drugs or foods or making the drugs or foods. Being able to understand reactions and how fast they're going to happen is really important. Otherwise, you could really mess things up. Parameter that affects reaction rate. We have a light stick, Pablo, and in the left it's an ice. In the right, it was moved over to a container of hot water. You see any different? Yeah, brighter than hot water. Javier, does that make sense? This light stick, you crack it and then the little reactants mix and then they produce light in the reaction. Does it make sense that the light stick's brighter than the hot water? Why? What's that? Faster. Things are happening faster. Things are moving faster. So yeah, you can generate more product faster. Right, I agree. Okay. There's some other things that or influence reaction rate. Here they are. Lewis, you can increase a reaction rate if you increase the concentration of the reactant. Yeah. We're going to find out products have nothing to do with anything. Increase the destiny, what would you guess? Increase the temperature. The other guys don't have much to do with anything. Especially when the reaction is Mallory. So you want to crank up the temperature. When we're cranking up the temperature, Mallory, what are we really adding? What are we really adding effectively? There's an H. Heat, right? So if you want to make things go faster, do you want to increase the reactants or the products? Everybody. They're reactants. So you want heat to be a reactant, and then if you add more heat, man, the reaction's going to go faster. So which one is it? Endo or exo, where heat is a reactant? Endo. Exo is where things get hot. So that means that heat had to be a product. Endo is where things get cold, so heat's a reactant. So it has to be endo, especially endothermic reactions. I think this question, Shelby, makes the most sense if our reactants are these solids. And, there could be these hard pellets, or we could smash them up or something. Increase the what of these reactants, and the reaction will go faster. I think it's hard to visualize unless you realize that for reactants to make products, they have to physically touch, collide, interact. They have to physically do it. So you can enhance that, increasing the what? Surface area, right? Because whether it's density or volume, that's whatever that compound is. But surface area, you can smash it up, right? Right? And then I think it makes the most sense with solids, right? Because they could be these hard pellets, or you could smash powder, things would react better. How about use a, Victoria, catalyst? Big money in catalysts. All they do is make reactions go faster. You get to equilibrium faster. You don't get any more product, but you get there faster. A lot less energy. So if you can figure out a catalyst to make whatever drug or whatever commercial product you're after, you can save a lot of money. Writing rate laws. Now this rate law is what you're going to use to predict how fast this reaction is going to happen. What's the effect of changing these concentrations? Or if these concentrations are these amounts, how fast will the reaction go? So the book has its idea. It says it's an equation, relates the rate to the concentrations of the reactants in the products raised to various powers. Okay, so here's our overall reaction. Matteo, you'd say what are the reactants in that? Yeah, the capital letters or the small letters, though? The capital letters. The capital A and capital B are the reactants. What was the term, Amanda, for the little letters, A, B, and C? What were they called? Or what are they? Anyone know? I don't think we've ever used this word when I come to think of it. Maybe we have. The stoichiometric coefficients. Those are the numbers out in front that you mess with to balance the reaction. Those are the numbers you use in the mole bridge, right? The coefficients. They're technically called stoichiometric coefficients. Anyway, as if you need that. But if this is your general reaction, then this is all you do is you write rate equals K, and then in brackets you have each reactant, and you raise them to some little exponent, X or Y. Okay, so it's not so bad. But we have some terminology, Sylvia, to get through. What do they call the K? What do they call that? The rate constant. They call K the rate constant. It never changes. It doesn't matter what the concentrations of the reactants are. It's just a number. Okay. How about the brackets, Ray? What do these brackets mean? They're supposed to mean something. Starts with C. Concentrations. Those are the concentrations of the reactant. Supposed to mean. Usually they use molarity, but that's okay. The meat of what we're doing today is to find these exponents X and Y. They call them the orders of the reactants. So like X is the order of reactant A. Y is the order of reactant B. The overall order, anybody know? Add up X and Y. And that's the overall order of the reaction. Just add up the exponents. But anyway, how do you find these exponents X and Y? You have to do experiments. So these questions are going to be long and big because they have to give you all this data for you to figure out what X and Y are. But it's not so bad. You'll see. Do products ever show up in the rate law? So Jessica, I gave you this general way of writing the rate law. Does it look like products ever show up? No, right? They never show up. So you're never going to write products in a rate law. Before we start figuring out how to get our exponents X and Y, Vanessa Vasquez, let's see if we remember how to do some math here. 4 equals 2 to the X. X is, she says, 2. Everybody agree? Yeah, because 2 squared is 4. How about Jessica Vaughn D? X is 1. Yeah, any number raised to the 1, you get itself again. Nick, how about C? You said it pretty quick, is he right? Yes. 3 times 3 times 3 is 27. Yep, so 3 raised to the 3rd. Ariel, looks like a trick question, but possible. 0. Anything raised to the 0 is 1. Someone mentioned a half. What is a half? That means square root, right? So don't worry. We're not even close. Don't even worry about that. So anything raised to the 0 is 1. So that's the math. Not so bad. Okay. Now let's see how we're generally supposed to approach these problems. So this is just in general what it's going to look like. Notice in the number 2 they give us a bunch of numbers for experiments. Okay. So they give us this overall reaction. Alexa, how would you write the general rate law? I'll get you started. Rate equals, what would you write? K, and keep going. Yeah, the E in brackets, raised to the X, keep going, and then F in brackets. See, all she's doing is picking out those reactants, right, and putting them in brackets. That's all. Okay. Then they give you this table. Notice what's in that table. They give you the concentrations of the reactants, and then in the third column, they also give you the rate. Fine. So how do you get this X and Y is what we're after. You do the number 3. You pick 2 experiments where the concentrations aren't changing for one of the reactants. It's constant. So, I don't know, just pretend that you know what these numbers are. And if we looked at experiment 1 and experiment 2, these 2 numbers were the same. Just pretend. Okay? So we're just going to compare experiments 1 and 2. So E is kept constant. What does that mean? That means those 2 numbers are exactly the same for the E, for experiments 1 and 2. So what happened to F? So you have to take a look at these 2 numbers. See what happened. Use your calculator, because they're not going to be easy numbers. Divide it. Divide the 2. See what's changed. You'll probably get a 2 or 3 or 4 or something, right? So you divide them out. You get your number. In this case, you got a 2. It doubled. And then you got to divide the rates. Right? Again, they're not going to be easy numbers. Just use your calculator. You get a 2 or 3 or 4, or maybe they stayed the same. Who knows? You divide the 2 rates out. And in this case, they also doubled. So then we're supposed to write a relationship. The relationship you're going to write is going to look like this every single time. 4 equals 2 to the X or something. Okay? So let's see how this looks. Now what I want to do, though, so I don't get lost, is I'm going to follow a general rate law. Okay. So first I want to write, okay, how did the rate change? Because that's first, going from how did my rate change? Well, my rate doubled. So I put in what number? 2. My rate doubled. Okay, the next thing is the K. Does it equal? And now the K. So that was my rate part. Now my K part. How does K change from experiment 1 to experiment 2? The K. It's a rate constant. So you can just put in a 1, I guess, right? We don't know what K is.
So would it be that number?
It's whatever the number is. Yeah, we don't know what the number is. It could be 7. But 7 goes to 7 doesn't change. It doesn't matter what it is. So that's going to be a 1. The next guy we're supposed to look at is E. Okay, now what did E do? E was kept constant. So what number do we put in? 1. Right? But don't forget to put in the X. It really doesn't matter, though. Right? Because 1 raised to any power is going to be 1. But still, let's just, so we don't lose anybody. The next thing you're supposed to mess with is the F. Now, how did the F change? It doubled, so we put in a 2. But don't forget to raise it to the Y. It's just starting to look like one of those equations, right? Because now we'll clean it up a little bit, and you can write 2 equals 2 to the Y. Right? That's the equation that we end up writing. Okay. And your Y is just going to be what? 1. Right? Okay, but anyway. This is another possibility. Okay? So again, follow the rate law. Do the rate, compare the rates first, and then your K, then your E concentrations, and your F concentrations. So how did the rate change? What number should I put in for the rate, Adrian? The rate quadruple. So we're going to put in a 4. We divided those 2 numbers, those 2 rates out, and we got a 4. Okay, how does K change? We put in a 1. Okay, now we're supposed to look at E. Javier, what do we put in for E? 1, because it didn't change. Technically, we should put in a 1 to the X, but the same. And then for the Lewis, for the concentration of F, how did it change? Double. 2. And it has to be raised to the Y, according to our little rate law. So our equation, you do some simplifying a little bit. 4 equals 2 to the y. It could end up looking like that. Okay. And then our y would be 2. But here's another possibility. So destiny, we compared 2 experiments. And first we were supposed to compare the rates out. How did the rates change? What number would you put in for there? Destiny, a 1. Right? The rates stayed the same. Next you'd write a 1, because we're trying to follow the K. Right? Just try to follow the rate law. Then you don't get lost. Right? Okay, K didn't change. And then you look at E. How did E change? Oh, it stayed constant. And then the last term would be 2 to the y again. You end up having 1 equal 2 to the y. In that case, y is going to be 0. But right, the hard part, I think, is getting the equation. Okay. So let's say we figured out what x and y are. How do you get that number for k? They don't. They never, ever do. It'd be nice. Mallory, do you have an idea? Nope. Glad I'm honest. Oh, you're getting on track there, right? This rate law, we just figured out numbers of doing experiments. Just pretend, I don't know, this guy's 2 and this guy's 1. I'm just making up numbers, right? And then you pick any experiment, because does the K ever change? No. So let's pick, I don't care, let's pick experiment number 3. Then you're going to plug in a number. If you pick, let's clean this up a little bit. If you pick experiment number 3, you know what the rate is. It's this number. You know what the concentration of E is. This number. You got to square it, though. You know what the concentration of F is. It's that number. And you solve for K. It doesn't matter what experiment you pick. You just solve for K. You get the exact same number every time. Okay? Just make sure you know, with your concentrations of your reactants, raise them to the right power. Otherwise, you're going to mess up. Okay? But first, you got to figure out what those powers are. Then you can figure out what K is. Started. Shelby, here's a question, but notice there's a big list of experiments or anything. They just gave us the reaction, and they gave us the rate law. They just said exactly what the rate law is. What reactant is missing? Shelby, what reactant is missing? In the rate law, what reactant is missing? So we have K, H plus, right? You see that? It's here, but it's not in the rate law. Actually, we could have wrote it. We could have wrote H plus, but it needs to be raised to what power? Because this is the rate law. It's kind of a trick question. All right? Because anything raised to the 0 power is 1. That's why in what's circled here, it's not there. Because it's raised to, it's raised to the 0 power, which is 1. Okay? So they told us what the rate law is. So what is the order with respect to each reactant? So, how would you, Victoria? We've got permanganate to C2O4, and we've got H plus. What is the order for each reactant? What is the little exponent? So permanganate, you'd say what, Victoria? If it was 2, they'd have to have a 2 written where? Right there, right? Anything to the 0 is 1. It's hard to see. When they write this stuff, it's always assumed what's up there? A 1. It's always assumed. And we never write the 1. We should, since there's such a big stinking deal, these orders are. but they don't. So the order for permanganate is 1. The order for everybody is 1 again. Now here's a trick question. The order for H plus is 0. Okay. What's the overall order, Matteo? What's the overall order? Trick to that was just add them all up and you get 2. Just add them all up. All right. This is more like the homework, right? And you're going to see this a lot. They give you all these experiments. And there's a lot of reading in there, but pretty much the only thing that matters is write the whole rate law. And they even want to know a number for the rate constant. They want the entire rate law. Amanda, let's start out by just writing our general rate law. Otherwise, we don't have a little guide for anything. So how would we, in general, write our rate law for this? You'd write what? First you write, over here. Keep going. Yeah, not E, though. Pick CLO2, right? Raised to the X. And keep going. What's the other reactant? Hydroxide. Everybody raised to the Y. And then on the left-hand side, you're supposed to write the word rate. Okay, so this is what we're generally supposed to follow. Okay. So Sylvia, we need to pick 2 experiments where one reactant what? Pick 2 experiments where one reactant stays constant. Okay. So Ray, you see them? See 2 experiments that we could compare? 3. Okay, he sees 2 reactants and he sees one reactant in there where its concentration doesn't change. That ClO2 doesn't. Okay. So Genevieve, let's not skip any steps though. I want to plug stuff into this, see how things change following the rate law. So first I'm going to see how the rate changed. Let's not skip any steps, Genevieve. Let's write in what number over what number. Yeah. Okay. 0.00276 and the 0.00828. Now you notice I wrote which one on top? The bigger one. Because 4 equals 2 to the x. Right? You don't want decimals in there. You have to use your calculator then. So always write the bigger one on top and life is going to be so much easier. Okay, so we just compared the rates. Now let's compare the k's, Jessica. So we're supposed to write what? Oh, yeah, but first, I don't want to skip any steps. You're right, Jessica, you're right. But I want to write 1 for the k. Okay? Now let's do your ClO2 part. What was she saying? Right, what over what? 0.02 all over 0.02. Everybody raised to the x. Right? All we're doing is comparing experiments 2 and 3. Vanessa Vasquez, now we got okay, we did the K. Next was the ClO2. Now we got to do the hydroxide. So you're going to write what? Bigger one on top. 0.09. 0.03. Good. Don't forget to raise it to its power. Now we got to do the math. Let's see. 0.00828 divided by 0.00276. I got 3. Yeah, thanks. 3. 3 has to equal 1 times 1 to the x times, that should be 3, right, to the y. So what does this look like? 3 equals 3 to the y. Yeah, we got our y. Okay? So let's get our x. What two experiments, Jessica Vaughn, do you think we should compare? Erase these. What two experiments do you think we should compare to get our x? She says 1 and 2. Oh, yeah, I see it now. All right? Because then those two aren't. Everybody see why she picked 1 and 2? Okay. Do the exact same thing, Nick. So
Over.
yeah. Something that looked weird there. 0.0248 is bigger, so you're fine. And then 0.00276. Okay. And then Mariella, what do I suggest writing next? The one for the comparing the K's. Now let's compare the chlorine dioxides, Alexa, and you'll write what? 0.06 over 0.02, and that needs to be raised to the x. And then we got to compare the hydroxides, Adrian. Comparing the hydroxides. Yeah, raised to the y, or raise it to the 1, because we know what y is now. But you get the same result no matter what. 0.0248. Divide that by 0.00276. And I got about 8.98. Yeah, just write this out, then we'll see. 8.98, 0.06 over 0.0, oh, forgot about my 1. 0.06 over 0.02 is 3 raised to the x. And then that'll be 1 raised to the y. Okay, now you're wondering about the 8.98. They're going to want you to what? Round it to 9. Yep. Okay, so we really end up with 9 equals 3 to the x. Is 2. We got them. Okay. Now we got to get the k. They want us to write, notice the question. They want us to obtain the rate law and the value of the rate constant. So if they say obtain the rate law, that means this thing right here. Right? You got to know what k is, and x and y. Okay. So let's get k. Now remember what our rate law is so far. Our rate law is rate equals k ClO2. Now we know x is 2, and we know the y is 1. So this is where we're at so far. We got to get our k. So Pablo, what was suggested, I don't know, 10 minutes ago? To do what? Yeah, plug in, pick any one experiment, because you can get the same k no matter what. So what experiment would you like to plug in the numbers for? Number 1. He says number 1. So let's use data from experiment number 1. Doesn't matter which one. So, Javier, according to experiment number 1, what's the rate? 0.0. And what do I put in for the k? Just k? I don't know what it is. Okay. And then the chlorine dioxide, Lewis, what's its concentration? The chlorine dioxide, the ClO2.
Isn't the rate 0.028?
I was trying not to have to scroll up. Did we read it wrong? Oh, yeah. There's our rate. 0.0248. Whoops. I should have scrolled up to make sure I forget who screwed up. 0.248K in ClO2, everybody, is what? And don't forget to raise it to the power. And the hydroxide is 0.03 raised to the 1. Now let's just check to make sure. Chlorine dioxide is, there's 0.06, and hydroxide is 0.03. Good. Okay. Now you got to get your K. We'll have 0.0248 equals K. 0.06 squared is about 3.6 times 10 to the negative 3. All right. So how do you set K? Just divide 0.0248 by those two numbers, right? 3.6 to 10 to the negative 3 and 0.03. So if you do this right, somewhere around 230 or so. Somewhere around 229, 230. Okay? Okay? But really not quite done because they want the rate law. So you should really write it. Right? Rate equals, now what's K? 230. The next thing you're supposed to write are the concentrations raised to their powers. So ClO2 raised to what power did we figure out? 2. And hydroxide raised to, we found out the Y was a 1. There's our answer. So if you know what the concentrations are, you can use the rate law to figure out what the rate's actually going to be. Okay. That is the rate law. That is our final answer in green. Okay. Okay. So what did we do? First we wrote the general rate law, and then you got to start comparing experiments where one reactant's not changing its concentration. Okay? And then we just plug in those changes into the rate law. Okay? It's online. Okay, let's try. It's online, man. Use the following reaction. So work out this one now. Okay? Work out this one. First, write out the general rate law. Okay? Write out the general rate law. And then start comparing experiments. But it all starts, I think, with writing the general rate law. Otherwise, you're not going to have a guide. Okay? Okay. Anyone not sure where to start on this? Okay. Write the general rate law, and then start comparing experiments. Let's get you sure we're okay.
O is 1 and 3. 1 and 3 and
1 and 3. That's for X, not for Y.
No. The 1 and 2 is for Y. 1 and 3 is for X.
It really doesn't matter, right? You just compare them and plug them in. It'll work out on its own. Do you recognize what's bigger, 10 to the negative 2 or 10 to the negative 3? 10 to the negative 2 is bigger than 10 to the negative 3. Yeah. Well, you'll find out if you plug it in your calculator and get a number less than 1. See what to do? Yeah, and then plug in, good. Yeah, plug in how the rate's changing. Okay. Well, not 1 and 2. Yeah, it is. Yeah, we need more sunlight, don't we? Solar calculators. Okay. Hopefully, if you compared experiments 1 and 3, hopefully you got something like this. I don't know what the answers are, but
Would you run off the 4418 to the 4?
yeah, you will. Right? And see if you can get your X. Okay. I got 2 for Y. Hopefully you guys did too. Yeah. I don't think that's right. What'd you get for your X and your Y?
My X is 1 and my Y is 2.
Okay. And you plugged in, you picked in, first one, you plugged in the rate, the number for the rate. Okay. Equals K. I think you just, I don't know what the answer is, honestly. It might be really big. But. So if you compare experiments 1 and 2, somebody got X to be 1. So do all the work. They got X to be 1. Did anybody else get X to be 1? Yeah. Okay, so I bet you that's right. So let's see if we can get our K then. And folks like to pick experiment 1, so that's fine. The rate is 2.75 times 10 to the negative 3. That's equal my K. Yeah, that's fine. And then I got to do NO concentration, 1.2 times 10 to the negative 4. NO's concentration raised to the X, and we said X is 1. And then we have to do chlorine, 4.8 times 10 to the negative 5 raised to the 2. It's going to be a huge number. It's a very fast reaction. 2.75. Why isn't the answer in scientific notation? That'd be a lot easier. About 9.9 times 10 to the 2, 4, 6, 8, 9. To the 9th. All 9s, 9.9. So then you can finally write rate what was it? NO and then Cl2. Okay, so yeah, your K is huge in this question. Okay, let me show you. So there's our final answer. Let me stop this guy.